Hello again. You can keep eating, that's fine. Nate promised some very good dinner entertainment. So it's really a great pleasure for me to introduce Nate Benoit. Nate attended the University of Maine for an undergrad degree and also a master's degree in structural engineering, and went on to work for the Department of Transportation. He's been there for 23 years in the bridge program, in bridge maintenance, and currently in the multimodal program. He served in a variety of positions, including bridge designer, project manager, and assistant project manager. And I can tell you, I know a little bit about him because I was his thesis advisor as a master's student. So I always tell my thesis advisees, I always reserve the right to revoke the thesis. Of course, I've never had to do that before, particularly not for Nate. Nate is working on a very, very exciting project, and it is to design a new port in the state of Maine to allow us to build a whole new industry, the floating offshore wind industry. How to build ports that can actually design floating hulls that could be fabricated, put in the water and towed out to sea and moored to the seabed and eventually maintained from that same facility. That's not simple. There's not that many floating wind ports in the world that are operational right now. Actually, there are none that are specifically built yet for floating wind. However, there's an international race to build floating wind turbines. And floating wind technology was declared by the US administration last year as the fifth US Earthshot, which is a key technology to meet our climate goals and our energy goals as a country. So it's a very important technology. There's an international race to do that. And wherever you travel in the world, people are inventing and developing floating turbines. Why? Because there's so much wind farther from shore. To give you a sense, within 50 miles of the US shores, there's enough offshore wind capacity to power the country 4 times over. That's how much, and 80% of us live in coastal states. So, and then of that offshore wind resource, close to 2/3 of it is in deep water too deep to fix the turbine to the seabed. So the only option you have is to float the turbine. So how do you float the turbine that's going to last 500 years out in the environment, right? And that's the challenge. But also these turbines aren't, because you're building floating turbines, you're almost like building ships to hold up turbines. And so a floating turbine port is like a shipyard. And you can't build ships without a shipyard. You can't build floating turbines without a floating turbine port. So how do you design a floating turbine port? Who knows how to design one? Who knows what these floating turbines would look like 5 or 10 or 15 or 20 years from now? Not too many people know. Just to give you a sense of scale, I want you to ask you to guess, how big are the biggest floating turbines in terms of megawatt capacity today? Offshore wind turbines. The ones that are actually operating right now. Any sense? It's single turbine. 17 megawatts for a single turbine. Okay, that's how big these things are. Now, how big is a blade on a turbine like that? Just to give you a sense, how big is a blade, do you think, on a 15 or 17 megawatt turbine? Okay, 1 1/3 football field long. 1 1/3 football field long. That's a single blade. So if you put the two blades together, the rotor is almost more than 2.5 football field long. That's the rotor diameter. Now these things aren't tiny. So if you're going to build a hull that supports something like that, I want to ask you, how much do you think that turbine weighs on top, the turbine and the blades, on a 15 to 17 megawatt turbines? Okay. Any sense? Up to 1,500 tons, 1,500 tons, and that's way up in the air, right? You know, that's how do you actually build the hull that supports it? And that's what Nate's trying to figure out, how to build essentially a manufacturing facility for these hulls that makes them and deploys them. That takes into account the fact that turbines keep getting bigger and bigger and bigger. You don't want to build a port and find out after 5 years, oops, turbines are too big in the port. So that's what Nate's trying to figure out. So please help me welcome Nate, and let's see what he's up to.
Thanks, Habib. So I'm Nate, and as I was saying on my table here, the first time I met Habib, I walked into his office and I left with a job. I had an opportunity to work at the Composite Center. And then I also found my way back to MaineDOT and found my way working with projects for Habib, doing Bridge in the Backpack, as Ken mentioned, and other composite projects. And somehow I got recruited and talked into doing the sport project, of which I'm the project manager. So I'm going to try to, all right, so this is a classic Habib line. I put this in there for you. Where are we and where are we going? So we have Belfast, Searsport, Stockton Springs. This is the Mac Point facility or Sprague's facility. And here is Sears Island, uninhabited island, with a causeway that leads out to it. We'd like to build a port facility here where a jetty was constructed. Large number of people involved with the project. Starts with the governor on down through our commissioner. I'm trying to do two things here. I got my laptop. I'm trying to click and see if we can get this figured out. All right, so this is our project. We want to build a commercial scale wind port on Sears Island. And you can see many, many cranes, large, big, flat area that we'll need to be able to do the floating wind turbine, foundation construction, lay down areas and everything, et cetera. This is looking across from in-town Searsport. So this is what it would look like. So the project here is really 3 steps. And Habib has stated this before. You want to walk before you run. And there's an initial project that that's been in development for a while and through NEAV for New England Aquaventus, and that was to do a single project off of Monhegan. So one unit. The second step is to do a project through PTOW or Pine Tree Offshore Wind, which is a research array, also known as MIRA. That would consist of 10 units. Well, a single unit and 10 units would be 11, and that's not enough to justify the cost of a port. We're estimating the port project at $600 million plus a barge at another 150-ish million, almost $750 million. And to build 11 units, you never justify that level of federal, state, private investment. So the key step here is to get to commercialization. And commercialization would allow for up to 900 units in the Gulf of Maine to produce 13 gigawatts of energy, 10 for Mass and 3 for Maine. That's enough to power 4 million homes, 1 million homes in Maine and 3 in Massachusetts. So why are we involved at the DOT? Well, we have a 3-port strategy, and each year we apply for PIDP funds, and we do port investments in Portland, in Searsport, and Eastport. Our strategic plan includes supporting economic opportunities. Jobs are obviously important to the governor and to the state. There'll be a tremendous number of jobs to construct the port, to operate the port, and for jobs in the supply chain. The governor's had an offshore wind initiative, a roadmap, and many state laws to support it. MaineDOT, we own Sears Island, and there's been plans for a cargo port since the 80s. Here's a number of state laws that have been passed. The first one back in 2021, and that basically said that if there's going to be floating offshore wind, you can't do it in state waters. We have to protect the lobstering industry, of course. It's vital to our state. So floating offshore wind needs to be many miles out to sea into federal waters. And then LD 336, and that was for the research array, and that's for the state to procure 144 megawatts of energy. And then this big bill is LD 1895, and that's to procure 3 gigawatts of energy by 2040. And then LD 1847, this was put into everyone's concerned about the scenic vistas. The crane is going to be incredibly tall. The assembled wind turbine generators are going to be incredibly high. So this law was passed, basically saying there's nothing to see here. Don't look at those. Don't evaluate that. And then this last one, if you read the papers or whatever in the news, there was an LD 2266, which was allow us to be able to impact a man-made coastal sand dune on Sears Island. So this is LD oops, I got to click here. LD 2266, the sand dune legislation. And you can see this is a tiny little sand dune. It's 0.4 acres. There's 3 sand dunes on the island, 2 in the north. And this one here is man-made. And why is it man-made? Well, back in the 80s, when we wanted to do a cargo port, we constructed this causeway over to Sears Island. We built Jetty Road on the island, and we built this jetty. Well, as a result of constructing this jetty, naturally, sand was, started to accumulate there, and then the sand dune was built. And now we want to do our wind port and say, oh, you can't, it's got to stop all construction. Now, of course, that's silly. So we had to pass LD 2266 in order to continue to move forward. You can see in the outline, there's 2 different colors here and shaded. So the darker color is the port parcel. We also call it the transportation parcel. It's 1/3 of the island. This was a result of the consent decree back in 2009, where 2/3 of the island was put into conservation, and then the other 1/3 was reserved for the port. The port is shown outlined here in white. The reason why we can't move the port is the area here where it says deep water was already dredged. So back in the 80s, when we wanted to do a cargo port, we dredged 580,000 cubic yards, and we did ocean disposal in Rockland, outside of Rockland. Also on the island, there's a cell tower here, and they have a little plot of land. This road shown in white may be relocated. We have plans to push the road completely onto the transportation parcel. What that would do is it's a mitigation effort. It's an added expense to move the road. But what it would do is it combines both conservation parcels, and we think it can enhance safety by having separation of the port and those that like to use the island to recreate on. Floating is different than fixed. There's 2 ways to do fixed bottom. One is with jackets. You see, oops, I'm sorry. I meant to hit the laser pointer. So Block Island, for example, in Rhode Island uses these jackets. Monopiles are very popular. Of course, we have deep water that we have to deal with. And to be able to do commercialization, this is the Boehm lease areas, and these are all deep water where it's required to do floating technology if you want to, harvest the wind out here where the winds blow. They're incredibly strong and consistent, as Habib stated. Boehm has come up with these 8 lease areas, and there's enough energy here for 15 gigawatts. The goal for Mass and Maine combined is 13 gigawatts. So there's plenty of capacity here. This lease auction is going to happen in October of this year. We don't think all 8 will, I don't think the developers will invest in all 8. So we think that there'll be a second auction 4 years later in 2028. Shown here is the research array, or MIRA. This is this box. Just for reference, this is Penobscot Bay. We have Vinyl Haven, North Haven, Islesboro, and then up here is Sears Island. So it's got a direct shot to at least to these northerly lease areas. The challenge, though, is that Mass and Connecticut, they don't have ports that are capable of doing floating wind. They can do fixed. They have smaller ports, but nothing of the size of what we need to be able to do floating. So we believe the port, if it was constructed on Sears Island, and if we build the full project, we could serve all 8 of these areas, and that'd be energy again for both Maine and Massachusetts. This is State Pier in New London. This is a facility, and you can see blades not quite as big as the ones that Habib talked about, but approaching that size. You can see towers here, but this facility in Connecticut is only 40 acres, and what we need is 100 acres. So clearly the ports in Connecticut and Mass are not big enough. You also need access to deep water. This is the port in New Jersey. This is a 200-acre facility. This is being designed for the New York Bight market, but it's designed for fixed bottom. It is big enough, it has deep water, it could be used, but it's also too far of a tow distance to tow units all the way from New Jersey to the Gulf of Maine. It would make it economically infeasible to do. So we really need a port in Maine. The design criteria, as I mentioned, it's 100 acres. It needs to be flat, 1% grade, and that's primarily so that you can use SBMTs to move equipment throughout the port. You need to have access to deep water, 35 feet. You need unlimited air draft. You can't have any bridges in the way from the port until the final destination out to the Gulf of Maine. You need to, for heavy loading, 6,000 pounds per square foot. And a delivery berth, or a berth for a delivery vessel, and 2 wind turbine generator units, or 1,500 feet. The acreage, I said, is 100 acres, and you can see the breakdown there. You have admin, storage of components, fabrication of the hulls is 55 acres, or more than half is for the foundations. The total there is 100 acres, and you can see the different components, the nacelle, blades, foundations. That's a steel foundation shown there. We're also, the port can be able to use either steel or concrete. So this is what it looks. This is what it looks like. So we mentioned 35 acres laydown area. This is delivery vessel that would come into port. You'd have a crane to offload blades, nacelles, and towers that would need to be stored. You have this large ring crane here. So you have the delivery vessel, integration berth, and this is where a heavy lift semi-submersible barge would be located. Potentially a building for indoor casting of precast components or steel, whatever type of foundation you want to do. There's laydown area for precast components. This is showing a batch plant and space for sand, aggregate, and cement to be able to make precast components. You have this like assembly track at the port, and you'd be building these units. This is not, you know, the developer and the port operator would set up, but this is kind of a representative setup here. So you'd be building these foundations, moving them along, adding on components until you get the finished product here. And then you need to do the critical move, which is moving them onto that semi-submersible barge. Now it'd have to be a ballasted barge. You got to keep the barge at the same elevation as the wharf. Once you get it onto the semi-submersible barge, you take the unit, you bring it out into deep water, out into the bay, you sink it, and then you bring and tow back the foundation to the wharf side. And then we use this incredibly large ring crane. This will be one of the largest cranes in the world. And it'll be those, if you said 1,500 tons, the number I was going to say was 900 tons. So they do keep getting bigger. You need to lift at a minimum 900 tons, 800 feet, and at least 200 feet out. You need a very, very big crane to do that. And you need a very heavy, well-constructed wharf that's strong enough to be able to support that. And Moffitt & Nichols, our engineer, they're telling us again, 6,000 pounds per square feet. We have to deal with NEPA. We need to look at alternatives. We're considering Sears Island, Mack Point, or the no build. These are all, I've hired many, many different types of consultants to do all kinds of different documents. You can see them there as part of the EIS effort. So we're looking at 2 alternatives. Again, Mack Point, Sears Island are the 2. This is Sears Island here. You can see in purple, these are the uplands. You need to fill in the ocean and build a 6,000 pounds per square foot blue wharf to be able to have a port. Where's all the earth going to come from? You're cutting from the uplands and you're filling in the ocean. You need to build a 50 to 60 foot tall embankment from the bottom of that dredge through that area. It's going to be an engineering challenge to build, to do that filled land. Problem with Sears Island is there's a lot of wetlands, and you can see them in that light colored green. You also see in red the intertidal and subtidal area. There's a great number of impacts to be able to do a port on Sears Island, and that's our greatest challenge is the large number of impacts. The good thing about Sears Island is you can see we've already dredged it, and you can see the dark blue that's been dredged to 40 feet already back in the 80s. The Mack Point alternative hasn't been dredged. So this area, the dark gray, would all need to be dredged. They also need to fill in the ocean there to be able to construct it. It has wetlands, it has intertidal area, and there's a significant amount of impacts on Mack Point too. The challenge at Mack Point, the big thing there is Sprague Energy owns and controls most of the land. MaineDOT owns Sears Island. We'd have to pay to be able to rent the land from Sprague. Canadian Pacific has a railway that runs through the front, and they're already doing work to upgrade. They have no interest in being relocated. There's not enough space. There's a great number of tanks that need to be removed, buildings that need to be moved. Back Point is a challenge. This slide shows ownership. You can see there's a number of different parties. You can see in green is Sprague's land, yellow is Canadian Pacific, and red is DOT or controlled by the Maine Port Authority. I am showing that I'm out of time. I will, this is what happened in the 80s. This was the original plan. There was one point, there was a plan to have an industrial park on the island back in the 80s, a resort. Those ideas have gone away. Again, we're putting 2/3 of the island into conservation. It's really expensive, and we can do it two ways. We can build the whole thing, or we could build half. And one option on the table right now is to build it in 2 steps, build 50 or 40 acres, and then build the remaining part. Again, you add the numbers together, 600 plus the semi-submersible barge, you're looking at $750 million. How do we pay for it? Well, we're applying for federal funds. We were turned down by CPRG. We did get the state got money for heat pumps through that grant. We did not get money for the port, but we have 2 grants right now that are pending. One is PIDP, which is a $20 million grant that we'd use for engineering. And then the big one, we have our fingers crossed. We hope to hear prior to the election of the state getting an equivalent grant to what California got at Humboldt Bay. They got almost $500 million to do their port. Our ask is only $456 million of federal funds. Pete Buttigieg is here today, he's here tomorrow, and we are hoping that he comes through for us and we have a grant. If not, we'll probably have to wait 2 years to apply for funding. In terms of the schedule, we have a public meeting planned for September. We're applying for some permits through DEP in October this year. There's a lease auction, as I mentioned, in October. The grant announcements that I mentioned are going to be prior to the election in November. We're working on this draft EIS that we plan for first quarter of next year. Hopefully, if everything were to stay on schedule, we could be issued a permit in 2026, and then we'll be building this thing in 2027. And that's what I have for you guys today. So. I'm supposed to stay, take questions or afterwards?
Yeah, we're gonna do
Okay.
a Q&A session once the meeting is over.
All right.
Well, Nate's already talked about a lot of the things. I'm going to blow through some slides so we don't have to go through them. But this is a floating wind turbine. It's called a semi-submersible floating wind turbine. And I'd like you to see if you could find the school bus. Where is the school bus? You see it right here? Just to give you a sense of scale. So these things aren't tiny. Okay, and when Nate's talking about a really big crane, the biggest in the world, we need a big crane like the biggest in the world to do this. So so this is really big. So as Nate showed, these are prefabricated, and then, but how do they float? And how do they hold up a wind turbine? How many of you have sailed a catamaran? Catamaran is a boat with 2 hulls, right? Okay, how do you make a catamaran more stable? You can make the hulls bigger, right? And you can put them farther apart, right? And then you have a more stable catamaran. Well, this is not a catamaran, it's a trimaran. It's got 3 hulls, one on each corner, one here, one there, and one here. These hulls are full of air, that's what gives them buoyancy. And the tower, the wind turbine is in the middle of that catamaran essentially, or trimaran in this case. So we're making, the hulls could be made out of concrete or steel. If you make them out of concrete, then you can make them locally and create the jobs here. That's one thing we're trying to do. Once you tow it out to sea, because it floats, you could tow it out to sea. then you have to moor it to the seabed. You have to connect it to the seabed. And we use 3 mooring lines typically. You can see one on each corner, because these are mooring lines. They used to be made out of steel, but now we're making them out of synthetic mooring systems, which are 1/20th the weight of steel, composites in essence. And then how does the power get to shore from a turbine like that? Of course, the power comes down from a turbine, down the tower, and then it comes out the side right here and down the side, and then through what we call a dynamic cable. This is an electric cable that has a buoyancy module on it, and then the cable is fixed to the seabed right here. So when the turbine moves around, because it does move around as the wind blows from different directions, the cable will follow it. That's why you have a buoyancy module. Otherwise, you break your electrical cable. Now, these electrical cables that you see right here are called dynamic cables. And how many of these is there in a farm? Well, it depends how big the farm is. Okay, how many of you remember Maine Yankee in Maine, the power plant in Maine? You remember how many megawatts was Maine Yankee? Yes? Well, it was 1 gigawatt, roughly 1 gigawatt, about 800 megawatts. That was Maine Yankee. Now, that's 8. So if you're going to make 800 megawatts worth of floating wind turbines, how many turbines do you need to make a nuclear power plant worth of wind? Well, if you have 20 units, right, 20 megawatt units in the future, you take 800 megawatt divided by 20, what does that give you? 40. So if you have 40 turbines like that, you can replicate a nuclear power plant. That's what we're talking about. Now, how far apart do you put these? You put them about a mile apart. That's how far apart these are. And then, so how much space do they take up? You have 40 of them about a mile apart. About 7 miles by 7 miles, right? Roughly, or less than that. So a 7 mile by 7 mile area, you can put on a checkerboard, in essence. Every mile, you can put a turbine, and that's basically what a farm might look like. Okay. Now, you need 40 of them to do a 1 gigawatt farm. Do you remember what Nate said? What's the plan? What's the need in Maine and Massachusetts and New Hampshire? Roughly 13 gigawatts. So it's be 14 megawatt, 800 megawatt farms plus. 13 of these farms. So 13 farms, how many turbines do we need? 13 times what? Times 40 if you do one per turbine. So you're looking over 600 turbines, right, that you need for the all of New England. And that's the size and the scale of what we're talking about. But these things will be placed beyond the horizon. You remember the map that Nate showed? That map showed 8 different areas. These are all 30 plus miles apart, away from shore. So if you're 30 miles away from shore, do you see the turbines? You just don't. Okay, because they drop off behind the horizon. Actually, they gave a talk once to a number of high school students in Portland. There was about 800 school students there, and I asked them, how many of you can wake up in the morning, look across the Atlantic and see the UK? And 2 of them did raise their hand in the back. So my question was, what did you smoke last night? But in essence, we all know, at least most of us believe that the Earth is round. There's actually a group of people who don't believe that. They believe the Earth is flat. They call it, right? And they actually have a conference that every year they go to Texas and they talk about how the Earth is flat. And there's hundreds of them. They go out there and they're convinced it's a conspiracy theory. But well, we engineers, of course, believe that the Earth is not. But if you go far enough away, you're going to drop off beyond the horizon. And typically 30 miles will take a 15 megawatt turbines and you won't see it anymore. So by going 30 or 40 miles offshore, none of us are going to know these exist. Okay? And that's an important part of this technology and the floating technology. So let's see if I can move on. Where do we have deep waters off the United States coast? Where do we have shallow water? Deep water in this business is about 100, it's about 150 feet or more. So if you're more than 150 feet deep, you got to float the turbine because it gets too expensive to fix it to the seabed. Okay, so what you see in dark blue are the areas off the coast of the United States where the water is more than 150 feet deep. What's in light blue are water depth less than 150 feet. So if you look at the Gulf of Maine, where we live, what does it look like? All dark blue except this, this light blue sliver right over here. And that's very close to shore. That's within 3 to 4 miles of shore. No one wants to put them this close to shore anyway. So in the Gulf of Maine, the only real option is floating wind turbines. Now, if you go down towards New York and Massachusetts and New Jersey and mid-Atlantic states, you'll see a lot of light blue areas. So right now, there's a bunch of projects being built that are fixed to the seabed. They're being built in Massachusetts and other places right now as we speak, but no one has built a floating turbine yet off the U.S. coast. Okay, and that's the next generation technology. Now, if you look at the West Coast, floating or fixed? The dark blue everywhere, right? So the entire West Coast has to be floating turbines. So the floating turbine technology is important for the future, and that's why we're doing this. So this is our lab. I'm not going to talk about it, but how many of you know how we test wind turbine blades to make sure they don't break? Of course, sometimes they do break. And many of us have been reading what happened in Nantucket, right? One of them actually broke during installations, still trying to figure out. They're telling us it's a manufacturing defect, but this is how we test the wind turbines. Okay, this is in our lab at the university. It's 100. That's a baby blade. It's 165 feet long compared to what we would be using offshore. But that's how you test them. You run these tests for a month to 2 months at a time. That's equivalent of about 25 to 30 years of in service. That's how you find out that it's going to hold up over the 20 to 30 or 40 years, and you certify a blade design. So these facilities exist, and you get a chance to see them tomorrow. We also built at the university a wave wind basin. This is a wave basin where you can create waves of different frequencies but at the very back, you see a wind tunnel. That's an open jet wind tunnel in the back. So we can create essentially windstorms over wave storms in that facility and recreate ocean environments. And we do that at scale, of course. We're not going to test a 15 megawatt unit there. That would be a very big building. What we do is we test things at scale. We shrink things to about 170 scale, and that's how we test these units. And shrinking these things to 170 scale and getting meaningful information out of a test like that is a big physics experiment. That's really what we're trying to do, is get the physics right to be able to do these kinds of tests. That's the only facility in the United States that's capable of doing that. We built that specifically to drive this technology forward. To show you how the system works, you can see here, we can create waves of different frequencies and heights. And what's really interesting about wave scaling, if you're testing at 170 scale, a 1 foot wave in this basin is a 70-foot wave offshore at 170 scale. So it goes by the scale, geometric scale. So a 2 foot wave in the basin is a 140-foot wave offshore. Now that's a big wave, right? So that's what you could do here when you scale these things. So there's different designs of floating wind turbines being developed across the world. There's a race to do that. The University of Maine has over 70 patents in this technology space, and many others have also a lot of patents. So this is you saw this right here, but I want to give you a number. How much would it take to electrify heating and transportation in Maine? Okay, how much energy does it take? So in other words, if all of us want to drive electric cars in Maine, and all of us want to use electric heat pumps, how much renewable energy do we need? It's not all going to be offshore wind, of course, but how much renewable energy do you need? Roughly 5 gigawatts. So if you had about 5 gigawatts of offshore wind capacity, 5 nuclear power plants worth of offshore wind, we can all be buying electric cars, we can all be buying electric heat pumps and get away from oil. Okay. Of course, that's not what we're going to do. You're going to use a variety of renewable resources, not just offshore wind. You can use land-based wind. You could use tidal energy and wave energy and other forms of renewable energy, solar energy. But that's roughly how much you would need. I want to give you a number. How much offshore wind capacity is there within 50 miles of the coast of Maine? There's 156 gigawatts of offshore wind capacity. Now, that's 156 nuclear power plants worth of wind blowing off the coast of Maine within 50 miles. Okay, that's how much energy we have out there. It's very, very big energy. So 5 gigawatts is how much of that surface area of the Gulf of Maine within 50 miles. 5 gigawatt divided by what? By 156? 5 divided by 156 is what? 3%. So if we just harnessed 3% of the surface area of the Gulf of Maine and put wind turbines there, we can electrify heating and transportation in Maine. Just 3% within 50 miles. Think about that. We can get off oil essentially if we wanted to, but of course that's not going to happen overnight. We're going to use different forms of energy as well. I'm not suggesting we'll only use offshore wind, but this is an example of what you could do right here. So, so what's the research plan for us at the university is 10 years ago, we put the first floating turbine off the US coast. You could see it on the left-hand side off Castine, Maine. This year, we're going to put another one in. It's going to be 10 times the size and a much more improved design that we won a national competition for. And that's going to go off Castine as well. It's a quarter scale unit. And as Nate said, in 2030, we're going to do a 10 to 12 turbine array, 144 megawatts. And then commercial wind farms, we don't expect will start to be built in the Gulf of Maine, floating farms, till the early 2030s. 2032 plus is when we think it's going to happen. So that's a bit of a schedule of what we're talking about would happen here. And this is the very first floating turbine that we built 11 years ago here at the University of Maine. And it was a 1:8 scale of a full-size one. You could see the people under it, and you could see, even though it was 1:8 scale, this is not tiny stuff. And this is how we towed it out to sea. We put it in the Penobscot River here in Maine, about 6 miles south of here, and towed it down the Penobscot River, just like that with a tugboat. And then we had pre-installed mooring lines, and then we attached it to the mooring lines. We had a pre-installed undersea cable, attached it to the undersea cable, and ran it for a year and a half with about 50 sensors on board to see how it performs with the waves and the winds, to see if our numerical models really work. And this is what it looked like off Castine, Maine. There's a very beautiful lighthouse right there. And this is the very first storm we saw. Needless to say, we knew the storm was coming. It was called Winter Storm Electra, December 2013. Our team did not sleep the night before because we didn't know how well we'll do. And this is what it looked like on that morning. So what you see blown across is actually snow. This is not actually wind. This is not actually clouds. This is a wind. This is actually snowstorm. The wind speed exceeded 50 to 60 miles per hour gusts on that day. Can you see the turbine moving? Can you see it moving back and forth? You don't. So that's what we wanted to show. We wanted to show that it's stable enough that it's not going to move a lot and fatigue the turbine and the blades and so on and so forth. So we proved that our models work. We proved that the technology work. As a result of that, the state of Maine and the governor here signed into law a bill to procure 3,000 megawatt of this. But that's all started as a University of Maine research project. And that's how we got there right now. So the future of the state of Maine will have 3,000 megawatts of floating wind to electrify heating and transportation. A dream we started with close to 15 years ago. So it's happening. I tell everybody who work in our lab, eat well and exercise every day. We're in for the long run, okay? Because these things take time to do. But I wanted to show you what we've done over the years. The other thing that's also very interesting is how close this construction method is to bridges. How many of you have designed or been on a concrete bridge, pre-stressed concrete bridge? Okay, just about everybody's seen a pre-stressed concrete bridge. So we built these hulls just like we built pre-stressed concrete bridges. It's just a different geometry, but it is how we build them. By building them using pre-stressed concrete, they'll last longer in the ocean environment, and also we can make them locally and keep the jobs here in Maine. That's a bit of what we're trying to do with our technology. And I was told I had 0 minutes left, and I'm done. Thank you. So. We have a QA session. I think Nate and I will be both taking questions, right? So we're happy to take any questions. Yeah. Yeah.
Plan to defer to. I plan to. Is it even on? Check. This one. Check. I was gonna defer to you, Habib.
Oh, depends on the question, right, Nate? Yes.
So I think this is a question more for me, it's more for a board.
Let's get the microphone so the
Oh.
recording picks it up.
Thank you.
I think this is a. I think this is a question for Nate because it has to do more with the port. And I don't know the split between onshore and offshore, but I think that there's a considerable amount of offshore wind in Europe. And I'm just wondering, are there ports in Europe that you can look at and say, we need to basically do that here in the United States?
So yes, there are ports in our consultant Watford and Nicholas support them and visit them and but yes, the Europeans they've been at this for a little while with primarily with fixed bottom, although they've dabbled in floating as well. So yes, there is a port in Esbjerg, Denmark, for example. I think it's like 250 acres. But there's ports being considered all throughout the world.
If I may add to that, we work a lot with the European counterparts. There are no floating ports yet in Europe. They're trying to build them too. So there's a lot of experience with fixed bottom ports in Europe, but not floating ports. So, yeah.
Hey, Habib, I have a question over here.
Yes.
Great job, both of you, by the way. So you talked about the spacing of these offshore wind turbines, they're a mile apart. Are they designed to be aligned in a way that they work together to increase the energy based on their positioning? Or are they so far apart that they're independent? And if they do work together, then how do you control that in an auction basis? Are those zones designed specific? Are people purchasing a portion of the zone and they sell all together? How exactly is that plan to work so that the engineering and everything flows properly?
Yeah, these are excellent questions. And if anyone here is a sailor and you were done sailing, you know that if you're downwind from another sailboat, you're not in good luck, right? So they do shadow each other. There's some wind, there's some shadowing effect from one turbine to the other. And of course, the farther apart they are, the less shadowing you would get. So, but typically the rule of thumb is you want to be between 5 to 10 diameters away in line with each other, so you minimize shadowing. So it's not a real issue. So 5 to 10 turbine diameters. That's the rule of thumb. So it turns out that most turbines in mile is good enough. You do get some loss, but a mile is good enough. But the more the merrier. So in terms of how a plant is laid out, if you had 40 turbines, do you put them all in the grid, or do you put them all in an arc? It all depends on the site. A lot of it is not only dependent on the wind direction, but also dependent on the geophysical condition on the site. Where are the good locations where you can anchor these turbines to the seabed? And with these floating wind turbines, you want to have mud, both 40 to 50 to 60 feet of mud. So oftentimes you have to put them where the mud exists in essence. So you have to locate them not only because of where the wind is, but also where the geophysical conditions dictate where it needs to go. So there's a lot of considerations of how you orient them. And also you want to try to orient them to facing the prevailing winds. Okay, so if the prevailing wind is coming from the east, for example, or from the west, in our case, west to east, you want to try to, most of the turbines to be facing that, not to be shadowed. So basically the prevailing wind, which is where most of the wind is going to come from, the turbines are not going to shadow each other in that direction. If they shadow each other in not very prevailing wind, you don't lose as much energy. So there's also the direction of the prevailing wind also will determine how you lay out the farm as well. So there's a lot of considerations there, but very important question. Yeah,
Great, thank you.
sure.
Hi, I had a question for Nate. I was just curious, when you are doing the layout of your port, why is it sticking out so much onto the seabed? Like, if you have an island, wouldn't you want to minimize the impact on the ocean? Is it because of the dredging, existing dredging? But
So the challenge is just to get access to deep water. So
Okay.
you have to get out to where that existing dredge pocket is, where it's already been dredged to. So the land needs to be, reach that dredge pocket.
But is dredging that expensive? I'm just
Oh.
like, could you like
Yes.
re-dredge into that dredge?
Yeah.
Fill in the existing dredge so that the dredge is closer to the, no?
It's the right question to ask. And we've been asked before already by the environmental regulatory, both the Army Corps and DEP. So what we have is the goal here is really to balance the cut and fill and to remove, for example, we have one design that includes removing 1 million cubic yards of earth. So 1 million cubic yards of earth will take you a year if you have a fleet of dump trucks and if they can do a round trip every 30 minutes. If you have 10 trucks, it takes you 1 year to move 1 million cubic yards. And that's a pretty balanced cut and fill number. And that was the number that the consultants had given us. We've actually got it down to 0 right now, cut and fill. We do need some added earth because you need to surcharge the earth because you're gonna, fill on top of soft soils. You need to get a certain level of capacity. But if we bring the pier way to shore, we're gonna have a tremendous amount of excess material. It's gonna be incredibly expensive to remove all of that. You're gonna have to, again, take a fleet of dump trucks constantly, pulling it off the island. So from an engineering perspective, you wanna balance it. And from a financial point, you couldn't afford to bring it so close to shore because you couldn't afford to remove all that material from the uplands primarily. Dredging in Penobscot Bay is incredibly challenging. We tried to do the nav channels at 35 feet in Penobscot Bay. At one point, we tried to go from 35 feet to 40 feet. There's been tremendous opposition to any dredging in Penobscot Bay, primarily from the lobstering industry. If you remember, this is Islesboro, Vinyl Haven, North Haven. These are people that have resources to be able to challenge any type of project. I was trying to say that politely. We have an existing project to do a maintenance dredge of only 22,000 cubic yards. So 1/20th the amount of dredge that would be needed. And that project has been in existence for, over a decade. And that's just to do a maintenance dredge. So it's very contentious. The lobstering industry is very opposed to any type of dredging. So we'd like to try to do a project that doesn't have any for that reason.
I'll take the next question. Thanks for the great presentation, Habib and Nate. And my question probably is more for Nate. If at the end of service life, wind turbine blades get decommissioned, are there any thoughts when these decommissioned blades are brought back to port to be able to cut them up, perhaps shred them on site in such a way they can be transported in bulk and then they can be used for different processes? This is something, one of the technologies we're currently looking at actively in the Composite Center.
I don't know if I want to try to tackle that question. That's an area of it's not in my wheelhouse, to be honest. So,
Okay.
Be you.
Now this is a really good question, Roberto, and that's something that must be part of the plan.
Yep.
Looking at complete life cycle of these blades needs to be part of any plan that we put in the future.
Yep.
And that's becoming more and more of a requirement in European projects we're involved in. Europe is way ahead of us in terms of life cycle analysis and having criteria requirements and so forth on that. So recycling now is a requirement in every project. It's not just a what if we could. It's thou shalt, or you're not going to build a project.
Yep.
So Roberto is doing some really exciting work and his team on recycling the blades. Actually, he's taken the blades and he's ground them up into a small powder, if you wish, and put them in our 3D printers and printed with them. Some really very exciting material. So essentially almost taking the blades and printing something completely different with it in the future. So those kinds of technologies that Roberto is developing right now are really a key part of the future where we're going to take these technologies. So, but there's also technologies being developed to make recyclable thermosetting blades. So there's a technology right now to actually take thermosetting blades and then be able to kind of deconstruct chemically the blade back into its initial molecules and reuse those molecules for new technologies as well. That's being done. There's been a lot of hype about it. I'm not sure I'm convinced it really works yet at full scale, but there's another opportunity as well that's to use thermoplastic blades. And thermoplastic blades are 100% recyclable as well. So Roberto, your question is right on, and the answer is not should we, the question, no, we're going to have to. Yeah,
Right.
and,
Thanks.
yeah,
Thanks, Habib. Nate.
Are there any other questions? Thank you. It was great to be with all of you tonight, and we look forward to see you again tomorrow. Yes, I'm being told when you speak at a conference like this, you get a University of Maine mug. So congratulations,
These are
Nate.
spectacular, by the way.
Yeah. Cheers to offshore wind, right? How about that? Yeah, exactly. Thank you and have a great evening. Yeah.